So you can also use integrals to calculate the surface area of a 3D object, which is pretty cool. And this technique actually isn't too bad as long as you understand the concepts from the arc length video. Remember, there's two ways to calculate one of those tiny lengths along a curve, ds. One way is using the dx form, and there was the dy form as well. These are just two different ways of calculating that same tiny distance along a curve. And we're really going to be using these two things to calculate surface area. So make sure they make sense. And you also want to be pretty good on Shell's method. You want to make sure you understand the concept there. We do something in calculating surface area that's very similar to calculating volumes using shells. So, as always, for me, the best way to learn something is to, let's just look at a real actual problem with some concrete numbers, and we'll build this surface area calculation technique with this. So these surface area problems are going to read like this. We have the arc of this curve right here from 1, 1 to 2, 4. So it's not the entire curve, it's just a specific section, a specific arc. This one right here, along this curve. And we need to rotate this arc about the y-axis and find the surface area of the resulting surface. So this is very similar to the way we were thinking about creating 3D volumes. We just want to rotate this line about our y-axis here. And if we do that, we'll get this shape, but we only care about the surface area of this shape. We don't actually care about the volume in it. We just care about its surface area. So here's how we do this. We start by imagining a tiny distance, ds, on this curve here. And on our 3D model, here it is right here. And I'll select one of our two techniques for getting that ds. In this case, I'll use the x form. Alright, so this is just ds right here. One of our tiny distances on our curve. Of course, I want to figure out the derivative of our curve equation, dy over dx. So of course, dy over dx will equal 2x. So let me just throw that in here real quick. Okay, so what we have now is an equation in which I can plug in some x into this whole equation, and what comes out is the tiny distance on our curve at that x location. Okay, so that's our first step up here. From that small distance ds, using either the dx or the dy form to get us that ds. This is straight from arc length. Here's what we want to do next. Look at my model down in the bottom right. What we want to do is we want to take this small distance. It's so small that it's basically a point. We want to take this guy and we want to rotate it about this axis right there. Imagine swinging that point, swinging it around that axis. It would make sort of a circle. It would make a hoop. And imagine taking this small distance there, swinging it around that y-axis, and that would create a hoop too. And imagine that we kept doing this and we would get all these hoops. By adding up all these hoops, we would get the total surface area of this shape here. This is exactly what we were doing in the shells method, that 2 pi r that we're using to swing that tiny rectangle around the axis. Same here, but we're swinging basically a tiny length, ds, around some axis to create a hoop of length. And we want to add up all these hoops, these purple hoops over here, to create my total surface area. So I want to take this ds here, and I want to times it by 2 pi r, where r is that radius I'm using to swing, revolve, that purple ds around my y-axis. So on my main graph, here's the r for that little ds. Here's another ds right here. Wow. Here's the r we would use to swing that one. And each time we swing that little ds, we are creating one of those hoops. And if we add up all these hoops, we'll get the total volume. My picture sucks here, but hopefully you can imagine this. So of course I want to just add up all of these hoops. Getting a little bit ahead of myself, let's just figure out what r is. Of course I can't leave r there. What is the radius we're using to swing each one of these purple ds's around that axis? If I look at it, it's simply the x-coordinate of each one of our points. Don't forget, when you have a point, y is this vertical, x is this horizontal. It sounds easy, but we all tend to forget this. We like thinking of x and y as just, just 2 points and that's it. But we forget they really mean lengths. So each one of my r's is simply the x-coordinate. And there we go. This integral is completed. It'll add up each one of my hoop circumferences and get me that total surface area. So of course my bounds, being a dx integral, I want an x lower and an x upper bound. Well, my ds at my lowest x is going to be this one right here. And the x-coordinate of that point is our 1 from the problem. So I have an x lower bound of 1. And my last hoop will be produced by the ds right here. And the x-coordinate of that point from the question will be x is 2. And there we go. That's how you calculate surface area. Let me just fill in my step 2 and 3 here. So here's our steps for calculating the surface area. Let's go through and calculate this. Let's do this problem again, basically. But we'll use the dy form of the ds to base our surface area calculation off of. And we'll go through these steps and really just make sure we got them down from another angle. So let's form one of our tiny ds's using this. We're on step 1. And we're using the dy form. So here's our ds right here. And to complete it, we've got to consider dx dy. We have to treat x as our dependent variable this time. So to do that, I'm going to take our curve equation, just get x by itself. So here we are with that. Notice that I'm only looking at the positive version of it, because of course whenever we take a square root we have a plus minus radical y. But I only care about my positive x's here. I don't care about the negative x's. coming out of the second part of the equation. So only worried about the positive form. So because I need the derivative here, dx over dy, the derivative with respect to y, I'll just take the derivative of this thing. The power rule is a bit nasty, but we can do it. And there it is. Of course, we can throw this right in there. Alright, there it is. Remember, this whole thing just gets us ds. But in this case, I plug in the y into this equation, and it gives me the ds at that y. But same thing, we still want to swing each one of these ds's around the y-axis. So we're going to be using the same r's. And like we said before, each one of these r's is indeed the x-coordinate of each one of our green points right here. The problem is we can't just write 2 pi x anymore, because this is a dy integral. So we still want the x's, but I've got to use this. My radical y equation gives me those x's, it's just in terms of y. So that's exactly what we need. So I will write positive radical y right here. That will be my x and therefore my r. So this whole thing allows me to swing each one of these ds's about the y-axis to get my hoop. And of course I want to just add up all of these hoops to get my total surface area. Again, my first ds is right here. But what is the y-coordinate of this point? Well, the y-coordinate will be 1. And I'll keep packing those hoops on until I get to my last ds right here. And I want the y-coordinate of this point. That will be 4. So there we go. This integral will get us the exact same answer, surface area, as this one. But this is the dy form of it, the one that is based on the y form of the ds. And of course, same theme from the arc length section. If you're, if you're trying to calculate with like one form and it's not working out, try the other form. So 2 ways of solving the same problem. And that is how you calculate surface area. And I like surface area because it's heavily based on concepts that we've already talked about. So hopefully this video really helped you guys get a good conceptual grasp of how to calculate surface area. I'll have a practice video up so we can do some good practice problems to really solidify this concept.